Welcome to this video from the Causal Inference in Public Health Research Lab. In this video, I will show you how you can estimate the mediation effects for a simple mediation model using traditional mediation analysis in R. The outline of this video is as follows. First, we'll start with a recap of traditional mediation analysis. Then I'll tell you more about confidence interval estimation. And then I'll show you how to conduct a mediation analysis using R. Let's start with the recap of traditional mediation analysis. The goal of a mediation analysis is to determine what part of the total exposure outcome effect is explained by the mediator and what part of the total exposure outcome effect is not explained by the mediator. A mediation analysis decomposes the total exposure outcome effect into an indirect effect, which is the part of the exposure outcome effect that is explained by the mediator, and a direct effect, which is the part of the exposure outcome effect that is not explained by the mediator. So the indirect effect is the effect of the exposure on the outcome through the mediator. And when we think of the indirect effect in terms of this figure, then it represents the arrow from the exposure to the mediator and the arrow from the mediator to the outcome, because these two arrows together show how the exposure transmits its effect on the outcome through the mediator. The direct effect is the effect of the exposure on the outcome not through the mediator. So in this figure here on the slide, the direct effect is represented by the direct arrow from the exposure to the outcome. The total effect is the effect of the exposure on the outcome, both through and not through the mediator. Therefore, both the indirect pathway of the exposure to the outcome through the mediator and the direct pathway of the exposure to the outcome contribute to the total effect. We can also think of the total effect as the sum of the indirect effect and the direct effect. In traditional mediation analysis, mediation effects are defined and estimated using linear regression coefficients. We need to estimate 3 linear regression models to estimate the total, indirect, and direct effect. Before we go over the regression equations, I would like to remind you that in traditional mediation analysis, the total effect of the exposure on the outcome is often denoted with the letter C. The effect of the exposure on the mediator is typically denoted with the letter A, the effect of the mediator on the outcome with the letter B, and then the direct effect of the exposure on the outcome with the letter C prime. In this first equation, y represents the outcome, I1 represents the intercept, x represents the exposure, and the C coefficient represents the estimate of the exposure outcome effect. In the second equation, m represents the mediator, I2 represents the intercept, x represents the exposure, and the A coefficient represents the estimate of the exposure mediator effect. In this third equation, y represents the outcome, I3 represents the intercept, x represents the exposure, the C prime coefficient represents the direct exposure outcome effect. And in this case, it's the direct exposure outcome effect because this equation is also adjusted for the mediator. M represents the mediator, and the B coefficient represents the mediator outcome effect. Sometimes people wonder why we estimate the B path by also including the exposure in the equation. And when we take a closer look at the figure, we can see that the exposure is actually a confounder of the mediator outcome effect. So we need to adjust for the exposure to remove any potential confounding bias by the exposure on that B pathway. Based on the coefficients from those previous equations, the total effect in traditional mediation analysis is defined and estimated as the C coefficient from that first equation. The direct effect is defined and estimated as that C prime coefficient from the third equation. And the indirect effect can be estimated using two different methods. The product of coefficients method estimates the indirect effect as the product of the A and B coefficients, and the difference in coefficients method estimates the indirect effect as the difference between the C and C prime coefficients. Intuitively, the difference in coefficients method represents the difference between the total effect and the direct effect. So whatever is left over after we subtract the direct effect from the total effect should represent the indirect effect. Now that we have recapped traditional mediation analysis, let's talk about confidence interval estimation. Typically, we estimate normal-based confidence intervals for our regression coefficients. Normal-based confidence intervals are based on the effect estimate, a test statistic, and the standard error for the test statistic. To calculate normal-based confidence intervals, we need to assume that the effect estimate has a normal sampling distribution. When it comes to the estimation of confidence intervals for indirect effects, we have a problem. Because this assumption that the effect estimate has a normal sampling distribution doesn't always hold for indirect effects. Simulation studies have shown that indirect effect estimates actually have a skewed sampling distribution, and especially in smaller samples. Therefore, normal-based confidence intervals are not preferred for indirect effect estimates. When it comes to indirect effect estimates, we typically construct confidence intervals that can take into account the skewed sampling distribution of the indirect effect. While there are many different methods available that can take into account that skewed sampling distribution, in practice, the percentile bootstrap confidence intervals are most often used for indirect effect estimates. To estimate percentile bootstrap confidence intervals, we need to go through 4 steps. On this slide, I will briefly outline those 4 steps, and then after this we'll go into more detail for each of the steps. In the first step, we create a certain number, so let's say 1,000, new samples based on the original sample. We do this by at random taking individuals from the original sample and putting them into each of the new samples. In the second step, we estimate the mediation equations in each of those new samples. In the third step, we use the coefficients from those estimated equations to estimate the indirect effect in each new sample. If we estimate the indirect effect 1,000 times, then we essentially get a distribution of indirect effect estimates. Then based on this distribution of indirect effect estimates, we determine the lower and upper limit of the confidence interval using the 2.5th and 97.5th percentile of the distribution. So let's go through each of these steps in more detail. So in the first step, we create new samples based on the original sample. So let's suppose that our original sample had 10 individuals in it, and each of these 10 individuals have their own unique identifier. Then to create the new samples, we at random pull individuals from this original sample and put them into the new sample. It can happen that an individual is pulled into the new sample multiple times, and it can also happen that certain individuals do not end up in one of the new samples. So for example, in the first new sample here, individual 1, 2, 3, 4, 5, and 6 all made it in. Individual 7 is represented twice. We have individual 8 and individual 9, but individual 10 did not make it into this sample. If we look at the second new sample, we see that individual 1 didn't make it into the sample. Individual 2 is there, individual 3 is represented twice. We have individual 4, 5, individual 6 is represented twice, and then we have individuals 8, 9, and 10. So also individual 7 is not represented in this second sample. Then in the third sample, we have individual 1, 2, 3, 4, and 5 didn't make it into this sample. 6, 7, 8, and 9 are there, and individual 10 is represented 3 times. And we keep repeating this process until we have the number of samples that we want to create. So let's say we want to create 1,000 samples, then we repeat this process 1,000 times. In the second step, we estimate the mediation equations in each of the new samples. So these are the 3 equations that we went over earlier to estimate that C coefficient, the A coefficient, the C prime coefficient, and the B coefficient. In the third step, we estimate the indirect effect in each of the samples. So in the second step, we've estimated those regression coefficients, and we can now use those regression coefficients to estimate the indirect effect in each of the samples. So we can estimate the indirect effect either as A times B, so the product of coefficients method, or as C minus C prime, the difference in coefficients method. Once we have those 1,000 indirect effect estimates, we can create a distribution of indirect effect estimates. Now, I do want to note you don't actually have to create this distribution to estimate the confidence intervals, because we can also simply ask our software to output the 2.5th percentile and the 97.5th percentile. But just to kind of visualize what it could look like, here we have an example of that distribution of indirect effect estimates. In the fourth step, we determine the upper and lower limit of the confidence interval based on that 2.5th percentile and that 97.5th percentile of the distribution of indirect effect estimates across all those new samples that we generated. So just to summarize, indirect effect estimates typically have skewed sampling distributions, and that's why we cannot estimate the normal base confidence intervals that we're so used to from regression models. Instead, we need to estimate confidence intervals that can take into account the skewed sampling distribution of the indirect effect. There are many different methods available that can do this, but the percentile bootstrap confidence interval is most commonly used in practice. In this last part of the presentation, I will show you how to conduct a simple mediation analysis using R. I will demonstrate how to use R for traditional mediation analysis by showing how to apply mediation analysis in R to a hypothetical data example. In this hypothetical data example, the exposure was physical inactivity. In the dataset, physical inactivity was called phys_inact. The mediator was BMI, which was called BMI in the dataset, and the outcome was blood pressure, which was called BP in the dataset. We can visualize the data example in a figure, where we can see that physical inactivity is the exposure, BMI is the mediator, and blood pressure is the outcome. The hypothesis here is that physical inactivity transmits its effect on blood pressure through BMI. So in other words, individuals who are physically inactive on average might have a higher BMI, and individuals with a higher BMI might on average have a higher blood pressure. These are the descriptive statistics from the data example. The total sample consisted of 520 individuals. 254 were physically inactive. 266 were classified as physically active. The mean BMI in the total sample was 22.6. We can see that among those who were physically inactive, the mean BMI was 23.2, and among those who were physically active, the mean BMI was a little bit lower, 21.9. The mean blood pressure in the total sample was 135.2. In those who were physically inactive, the mean blood pressure was 138.2, and in those who were physically active, the mean blood pressure was a little bit lower, 132.3. When performing a traditional mediation analysis in R, the first step is to estimate the regression equations. On this slide, I'm showing you how to estimate the first equation. In the context of our data example, we're using the first equation to estimate the total effect of physical inactivity on blood pressure, or in other words, we're using it to estimate the CIPHR. The first line of code here on the slide indicates that we want to estimate a linear regression model. To do this, we use the GLM function. GLM stands for Generalized Linear Model. In this GLM function, we first specify our dependent variable. In this case, our dependent variable is blood pressure, which was called BP in our dataset. Then the dependent variable is followed by a tilde. After the tilde, we specify our independent variables. In this case, we only have one independent variable. Our independent variable here is physical inactivity, which was called phys_inact in our dataset. After we've specified our independent variable, we tell R that we're interested in estimating a linear regression model by specifying the Gaussian family type. And then finally, we need to tell R that it needs to use the blood pressure dataset to estimate our model. At the very beginning of this line of code, we see model 1 with a little arrow pointing towards it. This is just to tell R that it needs to save the estimates from this linear regression model. The second line of code, summary model 1, tells R to output the output of this first linear regression model. Then finally, if we want to estimate the indirect effect using the difference in coefficients method, so C minus C prime, we also need to make sure that we save the estimated C coefficient. And this very last line of code tells R to grab the coefficient from that output of model 1 for physical_inactivity. Here we see the output of model 1. The intercept indicates that physically active people, who are the reference group here, on average have a blood pressure value of 132.28. The coefficient, or the estimated coefficient for physical inactivity, 5.91, indicates that on average, individuals who are physically inactive have a 5.91 higher blood pressure value compared to those who are physically active. We can also see here in the output, in the very last column, that the p-value is well below 0.05. So in other words, physical inactivity and blood pressure are statistically significantly associated with one another. Here we see the code for estimating the second equation. In the second equation, we're aiming to estimate the effect of physical inactivity on BMI, or in other words, we use this equation to estimate the APAF. Again, we use the GLM function, but this time we specify BMI as the dependent variable. Physical inactivity is again the independent variable. We're still interested in estimating a linear regression model, so the family type is still Gaussian. And we again use the blood pressure dataset. We tell R to also save this model, but now under the name model 2. Summary model 2 tells R to output the model output. Also here we save the estimated A coefficient from model 2. This A coefficient is necessary to save if we want to estimate the indirect effect using the product of coefficients method, or in other words, as A times B. Here we see the output of model 2. The intercept of 21.91 indicates that physically active individuals, again, physically active individuals are the reference group, on average have a BMI of 21.91. The coefficient for physical inactivity of 1.32 indicates that physically inactive individuals on average have a 1.32 higher BMI compared to physically active individuals. In the last column, we can again see that the p-value for physical inactivity is below 0.05, indicating that physical inactivity and BMI are statistically significantly associated with one another. Here we see the code that we can use to estimate the third equation. This third equation is used to estimate the direct effect of physical inactivity on blood pressure, or in other words, the C' coefficient. It's also used to estimate the effect of BMI on blood pressure, or in other words, the B coefficient. This model we also estimate with the GLM function, as we can see in this very first line of code. Blood pressure, BP in the dataset, is our dependent variable. This time we have two independent variables, as both physical inactivity and BMI are our independent variables of interest. So after the tilde, we specify phys_inact plus BMI. The family type is still Gaussian, as we're interested in estimating a linear regression model, and the dataset that we're using is still the blood pressure dataset. At the very beginning of this line of code, we tell R to save this regression model under the name model 3. The second line of code tells R to output the model output. Then again, to estimate the indirect effect, we need to make sure we save the coefficients from this model. So the third line of code here specifies that we want to save that C' coefficient. We save it under the name CP to make sure we don't overwrite the C coefficient that we already saved from model 1. So to save the C' coefficient, we need to make sure that we specify physical inact, estimate at the end of this line of code. Then we also want to save the estimated B coefficient, so we do that under the name B, and we can see here at the end of this line of code that we tell R to save the coefficient for BMI. Here we see the output from model 3. The intercept of 109.9 indicates that individuals who are physically active, or reference group for physical inactivity, and have a BMI of 0, on average have a blood pressure value of 109.9. The intercept for physical inactivity of 4.55 indicates that individuals who are physically inactive, on average, have a 4.55 higher blood pressure value compared to individuals who are physically active when holding BMI constant. Then the regression coefficient for BMI of 1.02 indicates that for every 1 unit increase in BMI, the blood pressure value on average increases with 1.02 when holding physical activity constant. We can see here in the last column that physical inactivity and BMI are both statistically significantly associated with blood pressure. Here we see the code for estimating the indirect effect using the product of coefficients method and the differencing coefficients method. The first two lines of code are used to estimate the indirect effect using the product of coefficients method. Because we already saved the A and B coefficients after estimating models 2 and 3, the only thing we really have to do here is to tell R to multiply A with B, and to then save it under the name AB. We repeat the name AB under the first line of code to tell R to print out this AB estimate. For C minus C prime, we follow a similar strategy. Because we already saved C after estimating model 1 and C prime after estimating model 3, the only thing we need to do here is to tell R to subtract CP from C, and then to save it under the name CCP. We again repeat the name CCP to tell R to print out the CCP estimate to us. Here we see the output after running the lines of code on the previous slide. We can see here that the indirect effect estimate based on AB is 1.35, and the indirect effect estimate based on C minus C prime is also 1.35. When we're using traditional mediation analysis, for mediation models with a continuous mediator and a continuous outcome, A times B and C minus C prime will always give us the same effect estimate. However, when we have nonlinear models, this is not necessarily the case. And in those situations, we might not want to use traditional mediation analysis to do our mediation analysis. Instead, it might be better to use causal mediation analysis methods. But for now, let's focus on these indirect effect estimates. So the indirect effect estimate of 1.35 indicates that physically inactive individuals have a 1.35 higher blood pressure value on average compared to physically active individuals because they have a higher BMI. So in other words, this is the part of the effect of physical inactivity on blood pressure that is explained by BMI. Once we've estimated the indirect effect, we might wonder, is this indirect effect estimate statistically significantly different from zero? To determine this, we can estimate bootstrap confidence intervals. In R, we can estimate the bootstrap confidence intervals using the boot package. And 95% percentile bootstrap confidence intervals are the default in this package. It is important to note that the syntax that I'm going to go over now consists of two parts. The first part is the bootstrap function, and the second part is the command to run the bootstrap function. So let's take a look at the bootstrap function. So here we tell R to create this function that will save under the name bootstrap program. You can see that within this function, we essentially tell R to run those 3 regression models that we've already ran manually before, to save the coefficients from each of those regression models, and then in the end to return to us the product of A times B and the difference between C and C prime. Once we've specified that bootstrap function, we can run or bootstrap command syntax. Before we do that, we set a seed. And the seed we set for reproducibility. Because when we take those at random new samples, every time we would rerun the code, it would give us slightly different confidence intervals. So to make sure that R always starts pulling those new data sets for the bootstrap confidence intervals at the same point, we need to set a seed. So in this case, I set the seed at 1, 2, 3, 4. But you can really put any number down that you want. So maybe you want to use today's date, the year of today, maybe you want to use your own birth date. You can put any number down that you want. Just make sure you save it in your code here so that when you rerun it and you use the same number, you'll get exactly the same confidence intervals. So then we run the piece of syntax that tells R to actually run that function that we specified on the previous slide. So we do that using the boot function. We tell it to use a blood pressure data set. We tell it to use that bootstrap program that we specified on the previous slide. And R tells it to create 1,000 new data sets. Now you can increase this number to 5,000 if you want. The more you specify, the less variability there would be in the confidence intervals if you were to repeat this with different seeds. But R is a number that's often used in practice. Then after we specify this boot function and we save the results from this boot function under the name results boot, we can ask it to return the confidence intervals for A times B and C minus C prime. Here we see the bootstrap confidence interval for A times B. A times B was specified as that first quantity in the return function, so it's index number 1 when we run our boot.ci syntax. Here we can see that the confidence interval for A times B is 0.45 to 2.38. 0 is not within this confidence interval, so this indicates that the indirect effect estimate is statistically significantly different from 0. Here we see the output for the bootstrap confidence interval for C minus C prime. The bootstrap confidence interval for C minus C prime runs from 0.45 to 2.38. And it's perhaps not surprising that also this confidence interval indicates that the indirect effect estimated as C minus C prime is statistically significantly different from 0. Here we see the summary of the mediation effect estimates for a hypothetical data example. The estimate of the total effect was 5.91. The estimate of the direct effect was 4.56. The estimate of the APAF, so the exposure mediator effect estimate, was 1.32. The estimate of the BPAF, so the mediator outcome effect estimate, was 1.02. The asterisk behind these effect estimates indicates that these effect estimates were statistically significantly different from 0. The indirect effect estimated using the product of coefficients method, so A times B, was 1.35. The indirect effect estimated with the difference in coefficients method, so C minus C prime, was also 1.35. It's probably not surprising that the confidence intervals for these two effect estimates were also the same, and both ranged from 0.45 to 2.39. 0 was not captured within these confidence intervals, which indicates that the estimate of 1.35 was statistically significantly different from 0. It is important to note that in this case, the product of coefficients method and difference in coefficients method gave the same indirect effect estimates because we used a linear model to estimate both the APAF, the BPAF, the CPAF, and the C prime path. Now, if we use nonlinear models to estimate the effects, these effect estimates will not necessarily coincide. And in those situations, it might be better to use causal mediation analysis instead. This brings us to the end of this presentation. If you have any questions about the content of this presentation, then please feel free to reach out to me and/or Dr. Valente, and we would be more than happy to answer your questions.